at Institut Fourier in Grenoble, in France, and it will speak of the distribution of rational points.
Thank you. So
please.
First, do you hear me? Yes?
Yes.
Okay, so let me first thank the organizers for the invitation to speak. So I'm going to speak first about equidistribution. So what do I mean by equidistribution? So to describe this, I'll start with a sandbox example. So namely the projective space. So fix a norm, which I denote like that, on the real space Rn+1. And then we may define an exponential height. Which goes from the projective space over Q to positive real numbers, which is given by the fact that the height of a point with homogeneous coordinates x0 up to xn is given by the norm of x0 xn if x0 xn are coprime integers. Oh, I forgot to say that I have the window with the chat open, so if you wish to ask questions, feel free to use the chat for that. So anyway, with this kind of height, if I have a real number, which is, let's say, bigger than 1, then I can consider the set of points of height less than b. That is a set of points in the projective space with h of p less than p. So it's quite easy to check that the number of such points, the cardinal of this set, is given by a quite simple formula, namely the volume of the ball for the norm I have chosen with radius 1 divided by 2 times the zeta function taken at n+1. So this factor comes from the Möbius inversion times b at the power n+1 plus something which is negligible. Well, let me say that it is equivalent to this. Okay, and I can write this also as, let's say, 1 over n+1 times n+1 times the volume of the ball, which can be seen as the volume of the sphere, divided by 2, times the product over all prime p of 1 minus 1 over p times the cardinal of the projective space over fp, divided by p at the power n times b at the power n+1. So in some sense, you see that this term here, as I said, it's more or less the volume of the projective space over R associated to the norm I have chosen. And this term here, I can see has some regulating factor lambda p times the volume of the projective space over qp. Sorry? Is there something wrong?
No, nothing.
Okay. So this I can interpret as the volume of the adelic space associated to the projective space. Divided by n plus 1 times b at the power n plus 1. So this is a Tamagawa-like measure on the projective, on the adelic space associated to the projective space. And one idea, which in fact was suggested to me by a talk by Swinnerton-Dyer. So this idea comes from the talk by Swinnerton-Dyer. I quite remember well this talk by Swinnerton-Dyer, during which I realized that there was such a connection, that for such a formula to hold for any choice of the norms, so in fact, I have not described this here, but you can choose also p-adic norms for the projective space over QP. So for any choice of the norm, then the adelic measure I introduce, the Tamagawa-like adelic measure, has to describe the asymptotic distribution of the rational points of bounded height. Okay, so let me be a little bit more precise about what I mean by this.
Emmanuel, sorry,
yes.
could you write a bit larger?
Okay, so on my screen, there is no problem, but I'll try.
Thank you.
I'm not sure I see what you see, donc, so, okay, anyway. So if I take any finite set.
Perhaps, look, you could perhaps skip the last line. You know, I mean, on my screen, if I have the lines mentioned in the chat, then the last line's choice of the norms and how to describe disappears.
Okay, thank you for this remark. So anyway, so if I take a finite set, which is not empty, then I can look at the corresponding probability measure, which is simply 1 over the cardinal of x, the sum for p in x of the Dirac measure at p. So this is a probability measure on the adelic space. So here's the adelic space of the projective space, which is simply the product of the projective spaces over all places of Q. And then I can look at the limit of this measure as for the points of bounded height. So in other words, these measures converge weakly to the product over all places of Q of measures, let's say omega v, where, well, I denote by valuation of Q the set of places of Q. And the measure is given as follow. So at the infinite place, the volume of U is simply the volume of the inverse image of U intersected with the ball for the norm of radius 1 divided by the volume of the ball. Where, of course, pi is a projection from Rn plus 1 minus 0 to the projective space. And also at finite places, well, at finite places, there is a reduction map modulo p at the power m, let's say. And the volume of this inverse image of any subset is given as the cardinal of this set divided by the cardinal of the projective space over Z over P at the power M Z, where, so as I said, this is a reduction map. And X is any subset in the projective space. So this is a natural measure on the projective space over QP. Okay, and then we have that the points of, if you count the points of bounded height, then the limit of the distribution is precisely the product of this measure. So maybe let me show you a picture of that. Yes. So maybe if I can show you, yeah. So in this picture, I have represented points of bounded height on the projective plane, and the color of each point corresponds to the reduction modulo 2. So there are 7 points in the reduction modulo 2, and there are 7 colors. And the points are have a color according to the reduction modulo 2. And also, I should say that the size of the point is related to the inverse of the height. So if a point has a small height, is bigger. Okay, so in some sense, the point is that on this picture, all colors are more or less, there are the same number of points in each color in some sense, because the distribution between the reduction is uniform. Okay, and of course you can do at the same time reduction modulo 2 on some open set for the real topology, at least if the boundary of this open set is not complicated. So for example, you can look at the points in the red open set with a given color, and then you see that the proportion is exactly the one you expected. All right, so this is an illustration of this equidistribution for the projective plane. So now, well, when you think of that, I mean, it's a very strict condition to have such an equidistribution. So you may ask, well, does it hold for something else besides the projective space? So the point is that this equidistribution, in fact, holds for, well, already for smooth hypersurfaces of very large dimension when compared with the So with the degree, so the number of variables, well, number of variables has to be bigger than something like d minus 1, 2 at the power d, where d is the degree of the hypersurface. And it's also true for smooth, complete intersections of very large dimension. So it follows from the results of Birch. I think it was published in 1962. And also for complete intersection when the degrees are not the same, by a result of Browning and Hisbron, I think, which was published in 2014. So this use the circle method. Okay, and it also holds for generalized flag varieties. By this, I mean quotient G over P, where P is a parabolic subgroup of a linear group G. And this follows from the work of Langlands on Eisenstein series. And it was proven, well, more or less by Frank, Manin, and Schickel. In 1989, well, I proved the equidistribution slightly later. So in particular, it's true for any quadric. Because a quadric is an example of such a quotient. But for that, I have to be slightly more precise about the height one use. So the height has to be defined from an embedding in the projective space such that the corresponding line bundle is the anti-canonical line bundle on G over P. Oops. Okay, so it is also well known that in fact it's not true in general, that this does not hold, that there are in fact accumulation phenomena. So let me consider a slightly more general setting. So let me go to a number field and consider a projective smooth geometrically integral variety over K. Geometrically integral variety over K. And of course, I have to assume that there are a lot of points. So the points have to be Zariski dense at least. But in fact, well, it has to be almost like a Fano variety. So at least the anti-canonical line bundle has to be big and with some extra conditions, which are not completely clear. For example, maybe the correct condition would be something like omega v minus 1 is ample, the sum of an ample divisor plus a divisor with strict normal crossing. But the exact condition is not completely clear. But well, let's say Fano-like. So with a lot of rational points. In particular, I wish V to be rationally connected. So in general, even if you assume Fano, the limit of the measure of the counting measure, so again, probably I'm too low. So in general, the counting measure of the points of bounded height on V goes to something which is supported by a small set.
Too low, too low.
Yeah. Can't you move the chat?
I can move it away.
Yeah. So, okay, so what do I mean by small set? So let me give a definition of small set for this talk. So the point is that, well, if V is a projective model of V over some ring of integers OS, where S is a finite set of places. So it's not defined everywhere, but almost everywhere. Then for all placed not in S, we can define, as before, a very natural measure on the QP points of V. The natural measure given by the model, which again will be defined by taking that the measure of the inverse image of the reduction modulo power of the maximal ideal of some x is the cardinal of x divided by the cardinal of the model V over OV over this maximal ideal at the power k. Okay, then I shall say that a closed subset and in the adelic space is, well, negligible if for any such finite S on any model, the product of these measures of the projection of this set is 0, where this projection goes from the Adel set to the product for V not in S of V of KV. So in fact, I have in mind some kind of sieve methods to prove that, well, the volume of the set is negligible for all these measures. Okay, so let me give you two examples of such sets. So first of all, if I take a strict closed subset Z in V, then I can look at the adelic point of Z in in V, and this will be negligible. And also, thin subsets correspond to negligible subsets in the following way. So for that, let V, as before, be, well, almost Fano. So again, this means that omega V minus 1 is big, and there are some extra conditions on the cohomology of V. Then we may consider a morphism from X to V, which is finite, but with no rational section. Then one can look at the image of the adelic point in the adelic points of V, and this will be negligible in the sense I just gave by, I think, a result of Tim Browning and Lucran, which was, I think, published in 2017. So, in fact, the connection with thin subsets, so is that image of the rational points in V of k is said to be thin. In fact, this is a generalization of the previous example, because if you take a closed subset, then the morphism from Z to V is precisely of this type. All right, so the point is that if you have such a set with this condition, so again, I am going too low, so if you have a negligible set in that sense, well, then the number of points in that set, if there is equidistribution, the number of rational points in that set should be negligible. So I think I wrote it here. So let me say it again. So if there is equidistribution, and if n is negligible, then the number of rational points in n should be negligible as b goes to 0. Simply a consequence of equidistribution. Well, I shall say that n is accumulating, so loosely speaking, I shall say that n is accumulating if it doesn't satisfy that. If it is negligible, but contains a positive, give a positive, strictly positive contribution to the number of points. So let me give you two classical examples, now classical example of such accumulating subsets. So the simplest example, which was known for a long time, is simply if you blow up a point in P2, then the inverse, the exceptional line, the inverse image of the blown up point is accumulating. So this was known already, I think, to Serre in 1989, before that. And another example, which is an example of a thin accumulating set, which is Zariski dense, is due to Batirev and Chinkel. So in 1986, and then it was improved by Frey, Legrand, and so forth. In 2018, which is given by a hypersurface in P3 times P3, given by the equation sum of the xi yi cube equals to 0. So which is a cubic surface vibration. And in which, so how to describe it, I think the best way is to look at W in P3 times P3, which is given by xy cube times yi cube equals to 0. And then you have an obvious map from W to V, which maps points with coordinates xi, yi to the points with coordinates xi cube, yi. And the point is that the image of this morphism contains too many rational points. So conjecturally, at least, it is accumulating. And there are variants of these examples, which were done by Browning, in which you can prove that you have a morphism like that, which gives a thin accumulating subset, which is the escalance. So the idea, which was directly inspired by Manin, is to say, okay, remove this accumulating subset and look for equidistribution on the complement. So it is slightly frustrating because, in fact, there are very few examples for which really the equidistribution has been proven on the complement of the accumulating subset, even in classical case. So this was proven, for example, for some particular toric varieties, including the first example I gave above. But on the other hand, so which is more positive, is that for many examples, it has been proven that if you consider the cardinal of the points of Untitled outside a thin subset, this number behaves as expected, including the constant which is given by a Tamagawa measure. So if you believe in the principle I gave at the beginning, saying that if the number, the principal term of the number of points is given by a Tamagawa measure, then there should be some kind of equidistribution. If you believe in this, then these results is an indication that the points should be equidistributed outside on the complement of the accumulating subset. But okay, it has not been explicitly proven in most cases in which this result is known. So one of the reasons of this, I guess, is that, well, once you have proven that the result is true for one particular height, for a choice of the norms, then proving it for all norms, I mean, it's not something which will be published easily, let's say, because I mean it's somehow expected, and the techniques are not that different from the one you have been using. On the other hand, it is much more technical to prove that you have really equidistribution. Anyway, so it's from that point of view, I mean, I would like to have more examples where equidistribution is really proven. So I have now two remarks. So one remark I've already given, that is that in general, you really have to assume that the rational points is Zariski dense. Otherwise, of course, everything I said up to now is not very interesting. Well, you can look at the Zariski closure of the rational points and work with this Zariski closure instead. Okay, so that's the first stupid remark. And another remark, which is not as stupid, is that in general, even if the rational points are Zariski dense, in general, of course, you don't have a weak approximation. That is that the rational points are not dense in the adelic set. So, and this is really a remark of Swinnerton-Dyer, that if the closure of the rational points in the adelic space is not everything, then you have to use the conditional probability relative to this subset, to this closure. Because, of course, in some sense, you know that the points are in the closure of the rational point. So the measure you get is something which is defined, well, by taking the intersection with the closure of the rational point. And if you believe that in the situation you are considering, the Brouwer-Manin obstruction is the only one, the Brouwer-Manin obstruction to a weak approximation is the only one, you may use the set which is defined by the Brouwer-Manin obstruction instead of the closure of the rational points. I mean, if you prove, of course, if you prove the equidistribution relative to the Brouwer-Manin set, then this proves that the Brouwer-Manin obstruction is the only one. Because if you have that the rational points, the distribution of the rational point converge to that measure on the Brouwer-Manin set, then this means that the rational points are dense in this set. Okay, so let me just say at this point that in fact, Swinnerton-Dyer, the remark made by Swinnerton-Dyer concerned more precisely cubic surfaces. For which he had made some numerical experiments. So these were numerical surfaces for which there is some Brouwer-Manin obstruction to a weak approximation. So let me sum up the hope from this point of view. So you want to find a sequence of maps xi to v such that, so the point is that, of course, there is a first level of accumulation. And then when you remove this first level of accumulation, you get something which grows more slowly, but then you still may have something which is accumulating. So you have to remove that again, and again, and again. So in general, you will have a sequence, a stratification of your rational points according to this accumulating subset. So, okay, so such that at each step, the image of the rational point is accumulating, well, or I should say more precisely, the point is accumulating in V of k minus the union for j less than I of the image of the rational points over xj. And also, in the ideal world, you would hope that there is a equidistribution on the complement of when you remove all this, the image of all these maps. So of course, this is really hoping a lot. And the point is that Mannin's program provides a very precise conjectural geometric criterion to be able to detect such maps. Provide a conjectural geometric criterion to detect these maps. Which give potentially accumulating subsets. So of course, the point is that, okay, how many times do you have to repeat this procedure? Do you have to do it in infinitely many times? So of course, since the set of rational points is countable, if you have to remove countable set of subvarieties, I mean, it's not very satisfactory. So there is a very nice result by Lehman, Sengupta, and Tanimoto. Which answer to this question. So I think it was concluded by a paper which is still on archive and not yet published. So it's using the minimal model program, and it says that if V is Fano, so for this result, you really need V to be Fano. Well, all the morphism which, well, according to Mannin's program, which are conjecturally accumulating, factor through a finite number of them. So this says that at least conjecturally for Fano varieties, you only have to remove a finite number of thin subsets. Okay, so you can hope that from that point of view, that there is something which is still left in the variety after you remove all that, and you can look whether the remaining point satisfies equidistribution. Okay, let me conclude this part. What time is it? Ooh. Yes, I still have 15 minutes. So let me give a remark. So first, there are a few variants of this study. So another point of view is to use other. So up to now, I use, to measure the size of a rational point, I use a height, which is associated to the anti-canonical line model. So in fact, there is good reasons to look at other invariants as well. For example, there are other heights which are not related to the anti-canonical line model. So how the things are modified. So first of all, you do not get equidistribution if you use one height which is not related to the anti-canonical line model. But if you use all the heights, so by this I mean that you look the map which goes from the rational points to the dual of the Pika group of V, where let's say that h of p applied to L is some logarithmic height relative to L at P. So this is taking all heights. Well, you can ask the same question. Do you get equidistribution if you consider something like that? So there is a very recent result about toric varieties. So again, I do not think they really prove the equidistribution. So, sorry, Demir and Taklou Bigash. And it's just arrived on arXiv, where they consider all heights on toric varieties and prove that the asymptotic behavior of the number of points is more or less the expected one. And there is another direction, which was, well, suggested by the geometric analog, which is to consider slopes. So slopes, let me just say that slopes refine the notion of height. More precisely, if you look, for example, at the logarithmic height associated to omega v minus 1 at a point P, you can write it as a sum for I going from 1 to the dimension of the variety. Some slope at P with the slope being ordered in some way. Okay, so instead of looking at the height, you can look at the bigger slopes. So mu1. And in fact, the problem with that is that it is extremely difficult to compute slopes. Heights is not too difficult to compute heights, but to compute slopes, it's much more difficult. But some people managed to do that for flag varieties, for classical flag varieties. And again, it's something which is very recent. And there are situations in which it's much more natural to consider the slope. I mean, of course, I mean, there is an obvious, if I use the bigger slope, there is an obvious relation between inequalities between the bigger slope and the height, but it's much more difficult to use slopes. Okay, and to finish this talk, I would like to say a few words about the fine distribution. So what do I mean by that? If you look at the picture I gave at the beginning of the talk, when you look at the projective plane, you see lines. The lines are quite clear. So the question is that, okay, the statement about equidistribution is that if you let the bound goes to infinity, then there is equidistribution. But in fact, this equidistribution does not reflect the fact that if you look at the picture, you see the lines. So the things are not completely equidistributed in the same sense. So to be able to detect that, you have to, in some sense, rescale the picture to see the lines. So the point is fix some P in the real points of variety and choose a local diffeomorphism from some open set in V of R to, let's say, the tangent space at P. So for a given real number alpha, you may consider the set S alpha of B. So let me describe this as B at the power alpha times the image by phi of the set of rational points of height less than B intersected with the inverse image of the ball centered in 0 and of radius P at the power minus alpha. So this is something which is contained in the ball of radius 1. So in fact, I see that at the points of height less than B, rescaled by a factor B at the power alpha. So maybe I should show you an example of that, drawing of that. So, okay, yeah, I have a picture here. So the point is that, okay, I take that picture, which is not the projective space, it's P1 cross P1, P1 times P1. So the point is that I can look around a rational point and look at the distribution around a rational point. And what you see is that, in fact, there are two lines. And if you take some ball, which is with a small radius around this point, the only thing you see is that the vertical line and the horizontal line, and there is nothing else. So in some sense, also that P1 times P1 is something which is very homogeneous. If you blow up too much, you have something which is locally accumulating, which is not globally accumulating, but which is locally accumulating when you blow up around the point. If you choose another scale, if you do not blow up as much, then in fact, you get another distribution, and you remove these two lines, you get another distribution which is given by a hyperbola. So the color is not nice. Let me take another color. Okay. You get hyperbolas. And the distribution of points is given by these hyperbolas. If you choose the correct rescaling, of course, if you choose a rescaling factor which is small enough, because you have equidistribution, you still have equidistribution. So really the picture will depend on the alpha you choose. So the idea behind that is that you will get critical values of alpha for which the distribution of the rational points changes completely. And of course, also by the Dyer-Fontaine approximation principle, you get also a minimal value for which you have nothing, except maybe the point you chose at the center. So S alpha of B will be contained in P for B big enough. So this notion of critical values was pointed out to me by a former PhD student, Pajlo. And also, the point is that there are local accumulating subsets. as I described in the example, given again by morphisms. Phi from X to V. And in fact, Jijong Huang, who was my student, gave even an example with sin Zariski dense local accumulating subset, locally accumulating subset. For something which was a priori something very reasonable for a toric surface. So it was quite unexpected to me that even for a toric surface, it's possible to have thin Zariski dense subset which is locally accumulating. Okay, so let me conclude this talk by saying that thanks to the work of really many people, and I only gave a few names, and there are a lot of people who work on that, on Manin's program, during the last 30 years, I think now we can almost claim that for any given Fano variety, we can give a very precise interpretation of the distribution of rational points. By this, I do not mean that we are able for all Fano varieties to prove the distribution. I am saying that if you give an explicit Fano variety and you are able to describe precisely to prove the distribution of points, then you can interpret this distribution. But of course, the fact that now we are able to do that does not mean that there are no questions. So there are still a lot of open questions on one open question, which is very critical for me, is that what is the correct definition on Fano-like variety? So as I said, omega v minus 1 has to be big. I need the variety to be rationally connected. But right now, I'm not able to give an explicit definition of this property, which ensures that you will get enough rational points to hope that there is equidistribution once we remove the bad set. So right now, for me, it's really the most, because for example, if you take Fano varieties are very limited. In one given dimension, you have only a finite list of spaces. If you take toric varieties for which the results are known, there are infinitely many examples. So this means that there are a lot more examples than Fano varieties, but I don't know what is the correct condition to put right now on how far this picture holds. So let me stop here. I think I do not hear you, so.
Okay, let me thank you for your talk again. I suppose there are quite a few questions, but let me not start. What about questions by others?
So maybe I should ask the question, what is the correct condition you should put here? I mean, the people like, from algebraic geometry maybe have a very precise idea what should be the correct definition to ensure, for example, that the variety is rationally connected.
I don't understand. I mean, rationally connected as a definition.
Yes, but I mean, from the point of view of omega v minus 1 big.
Mm-hmm. Okay, I have one question about this theorem of Lehmann, Sengupta, and Tanimoto.
Yes.
this statement, is it over a given field or is it independent of the field you look at?
No, it's general. It's general. It's independent of the field.
So it's a statement over the complex field?
It's a statement of a field number field.
But,
And in fact, it's quite difficult. It's quite difficult to go from the complex setting to the setting of a number field, because you have a priori twists. You see, if you have a morphism X for phi from X to V, then you can have all the twists of these maps. And one of the tricky points, which was published in the last paper of them, is that, in fact, only a finite number of twists, you can reduce to a finite number of twists. And this is far from, for me, far from obvious. Because in some sense, the minimal model program gives that over C, the number of maps is finite. But then you have these twists, and you have to deal with these twists.
Oh, and so on a given, so if you start with the varieties of a Q, on a given number field, you'll have finitely many twists, but the number of twists will depend on the number of field you take.
Yes. Yes.
Okay. So you want to say a few words about slopes, because you didn't define slopes.
Oh, I didn't intend to go into that.
Right.
So the point is that in some sense, heights are only related to, yeah, it's here, are only related to line bundles. So in some sense, slopes are finer invariants which are related to vector bundles. So if you have a vector bundles, you can define a notion of, let's say, Arakelov metric on this vector bundle. And then if you use this data, I mean, at a given point and at a given rational points, you will have in the fiber of at this point of the vector bundle, you will have at the same times a norm at the infinite place, and you will have a lattice which is given by the norms at the finite places. And with the lattice, with the metric, then you can define the slopes by looking, for example, the classical invariants are, for example, the shortest vector in the lattice. Mm-hmm. So it's somehow related to that. And then you get these slopes, and if you define it correctly, then you get that, in fact, the determinant, which is the height here, is given as a sum of the slopes. Well, the logarithm of the determinant is given by the sum of the slopes. So I do not want to give more details, but the idea is to have invariants, new invariants coming from vector bundles. Well, not that new, in fact, I have not invented anything there. I mean, the invariance is due to boast on other people. But as I said, I mean, the point is that it's very difficult to compute.
And your notion of freeness of points, where does it fit in?
So the point is that the idea is that even if you have a bounded height, you may have that the slopes, the difference between the slope can get bigger and bigger. And in fact, if I go back to the picture, I have somewhere, yes, to this picture. If I go to this picture, the point is that if you look, if you look at a point which is here, so at a point which is not this point, but one of the points which is here. If you look at the slopes, they are more and more different. And these correspond more or less to the fact that you are on some locally accumulating subset. So the deformation of the lattice, you can see that as a lattice. You can think of the data as a lattice in a Euclidean space. if you look at it with this point of view, the lattice can be deformed. I mean, you can have a direction which is one direction in which you have short vectors and one direction in which you have very large vectors, I mean, in some sense. So, and this corresponds to what happened if you look at the data for the points here. But the problem is that it is very difficult to compute explicitly these slopes. But Tim and his collaborators were able to do that in particular cases.
Okay, so are there more questions? No, well then, well, thank you again for your talk.